igcse Physics. Paper 1. Radioactivity, Part 3. A scientist placed a radioactive source in front of a Geiger-Müller detector and measured the count rate every 20 minutes. This is the table. It shows the data. The scientist corrects the count rate readings to allow for background radiation. State two sources of background radiation. It may be cosmic radiation, radiation from the sun, stars. It may be radiation from rocks, buildings, radon gas. Maybe radiation from medical sources, nuclear waste, accidents, some foods, example coffee, bananas. Describe how the scientists could measure background radiation and correct the count rate readings. So scientists could remove the radioactive source, measure the background count rate, repeat the measurement, measure for a long time, background radiation is 30 counts per minute, and subtract this value from each reading. So the reading from the source minus the background count rate, background radiation. So plot a graph of corrected count rate against time and draw the curve of best fit. This is the curve of best fit. Use the graph to find the half-life of the radioactive source. Half-life is 600 and it seems like 640, so 320 is half, and it is about here. So this is like 38. Yeah, so 320 all the way to here. Seems like it's about 38 or 37. Yeah, so 35 to 42, which is 37 is in the range, 38 and all that. The radioactive nuclei in the source emit beta radiation. What effect does the emission of a beta particle have on a nucleus? So a neutron becomes a proton plus an electron, so it decreases the amount of neutrons but increases the atomic number, and the nucleon number, the mass number, stays the same. So yes, so neutron changes, neutron number decreases by 1, and a positive charges increase, number of positive charges increase by 1, and a neutron changes into a proton number increases by 1. Why radioactive sources can be dangerous? Because they emit ionizing radiation, 1 point, plus any of these which cannot be seen can damage or harm cells, can cause tumors or cancer. Describe how the risks of working with radioactive sources can be reduced. How can the risks of working with radioactive sources can be reduced? Equipment such as tongs use robotic handling, keep at a distance, EQ, and reduce exposure time, use shielding, work in a fume cupboard, wear film badge slash use monitor. Carbon 14 is a radioactive isotope of carbon. It has the symbol C14 is the mass number and proton number is 6. Number of nucleons is the mass number, which is 14. Neutrons is nucleon number minus proton number 6, which is 8. So 14, 8, and electrons in a neutral, so 6 and 6, 14, 8, and 6. 14, 8, and 6. When carbon 14 decays, it emits a beta particle. What is a beta particle? It is an electron. Beta particles are electrons. Carbon 14 has a half-life of 5,700 years. A sample of cloth contains 6.0 grams of carbon 14. What mass of carbon 14 will remain in the cloth after 11,400 years? So it is the double of 5,700. So 2 half-lives. So divide by 2, divide by 2. So 6 over 2 and then divide by 2 again is 1.5. 1.5. The carbon atoms in the cloth are mainly atoms of carbon 14, a different isotope of carbon. What are isotopes? So atoms with the same amount of number of protons, same element, same atomic number, with different number of neutrons, different mass number, different atomic number. The diagram shows a neutron colliding with a nucleus of uranium-235, producing a number of products. Name the process shown in the diagram. Fission. Nuclear fission. Explain how the process shown in the diagram can lead to a chain reaction. So it is split, neutrons are released, colliding and hitting with other uranium atoms and causing further fission. So nucleus splits, releasing neutrons which are absorbed by different uranium nuclei. Penalize ones if atom used for nucleus. Oh, I guess which hit are absorbed by different uranium atoms nuclei. So I said atoms by mistake. I meant nucleus splits, releasing neutrons, and they hit different uranium nuclei. The nuclei of these hit the nuclei of other uranium. So this process releases energy. Explain the form that this energy takes. Kinetic energy in the movement of neutrons, in the movement of neutrons and daughter nuclei, which are these nuclei that are formed, and of fission products. The energy released in this process can be used in a nuclear power station. What is the purpose of a moderator? It slows down neutrons. A moderator slows down neutrons. Complete the chart below to show the main useful energy transfers in a nuclear power station. In a nuclear power station, heat energy released by reactor into the heat goes into heat energy in the water or the steam, which in turn is the kinetic energy in a turbine, which turns into electrical or kinetic energy in a generator, into electrical energy in wires. So heat or kinetic or thermal in water steam, kinetic in the turbine, and kinetic or electrical in generator, electrical in wires. A teacher shows his class how to investigate the half-life of a radioactive source. This is the source, the GM detector, the meter, the counter. The readings from the counter need to be connected for background radiation. Need to be corrected. So the readings from the counter need to be corrected for background radiation. State one source of background radiation can be rocks, radon gas, space, cosmic, sun, medical sources from carbon atoms in living things. Describe the method the teacher should use to correct for background radiation. So describe the method. Remove the source or with no source present. Then measure the background count. Measure the background radiation, the count. Repeat, find mean average value. Subtract background from experimental values with the source. So get the background radiation when there is no source present, and then when there is a source present, just minus the background radiation to get the radiation, the count of the source. Every half a minute, the teacher records the count rate he corrects for background radiation and produces this results table. He corrects for background radiation and produces this results table. Okay, so I have to draw a graph. Let's do that. The isotope technetium-99 is a gamma emitter with a half-life of 6 hours. It is used as a radioactive tracer in medicine. The technetium-99 is injected into a patient's bloodstream and carried around the body by the blood. The radiation it emits is detected outside the body. So it is injected into the patient's bloodstream and carried around the body. It goes around the body by the blood, and the radiation is emitted and it is detected outside the body. Explain why technetium-99 is suitable for use as a tracer in this way. It is suitable as a tracer in this way because gamma can be detected outside the body, can pass through. So it will pass through, it will penetrate and be detected outside the body. And another point is half-life related, and that is long enough to get around the body for use as tracer. So the half-life is long enough. half-life related to patient safety. It falls to low levels soon after use. It doesn't continue emitting at high levels. It falls to low levels soon after it is used. So, firstly, gamma radiation can penetrate to the body and get out, and it is long enough to get around the body, and the levels fall low soon after use. Thank you very much.